guys, so for today's video we're going to be looking a little more detailedly into compounds. So now that we kind of know what a compound is and the types of compounds, we're going to look at how to actually find the formulas of compounds. So there's three possible types of formulas that you could have for a compound. You could have a structural formula, which actually shows how the atoms are bonded to each other, but that requires spectroscopy and other techniques to figure out how the bonds are actually arranged. And the ones that we're going to be focusing on today are the empirical and molecular formulas. So the empirical formula, like its name suggests, is based on experiment. So you could find it just by finding the percent composition of a particular compound experimentally. So the percent composition by mass is going to be a list of the percentages of the compound that's actually made up of each element by the mass. And you can actually use that to calculate the empirical formula. The molecular formula is going to be the actual amount of atoms that are in the compound. So the empirical is just the ratio. So if you had the compound C4H8, C3H6, and C2H4, these would all have the same empirical formula CH2 because they all have the same ratio of atoms. But they would have different molecular formulas because the molecular formula is the actual number of atoms. So C4H8 has a ratio of CH2. But it actually has in the molecule 4 carbons and 8 hydrogens. So its molecular formula is C4H8. So that is the difference. Now that we know kind of what they mean, let's do an example problem to see how to calculate the empirical formula. So suppose I have a compound that is 13.5% calcium. And we've got 10.8% oxygen, and we have 0.675% hydrogen. And we want to calculate the empirical formula. So how we do this is by using some definitions that we learned in the last video. So when we have percentages, these are just ratios. So we don't care about the actual amount of compound we have, so we just pick an easy number to work with. Like 100 is really nice to work with for percentages, so we just assume that we have 100 total grams of the compound. It doesn't really matter whether we pick 100 or 1,000 or whatever number is easy to work with, because we're looking for the empirical formula. We're looking for a ratio, not an actual quantity. So if we have 100 grams, that means we have 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. But in order to look at the formula of a compound tells us the ratio of atoms, but it also tells us the ratio of moles. Because like I said in the previous video, a mole is 6.022 times 10 to the 23rd atoms. So when you have a compound like, for example, C4H8, that's got 4 carbons in it and it's got 8 hydrogens in it. We know that, but you can also interpret the formula another way. So you can say that if you have 4 moles of carbon atoms, you also have 8 moles of hydrogen atoms. So the ratio works with both atoms and moles. But here we've gone from percentages to grams, but we need to go to moles. So how we do moles is we use the method of dimensional analysis that I've also explained before. So I'll show you guys the steps for calcium and then just kind of write it out for the other two. So right now we're in grams. We write what we have. We have 13.5 grams of calcium. And we want to get to moles. And what is our conversion factor from grams to moles? It is the molar mass. And so when you look at the periodic table, you're going to find the molar mass of calcium, and that is going to be 40.1 grams per mole. And remember those units, grams per mole, that's important. So we want the grams to cancel because we want moles. So since we have grams in the numerator here, we want moles to be in the denominator. So we can put 40.1 grams in the denominator, And how much is 40.1 grams? It is 1 mole. And this is great because our grams will cancel out, and now we only have moles. So we just have to perform this division. And then we get 0.337 moles of calcium. So I did a similar process for the oxygen and the hydrogen and ended up getting these molar quantities. We have 0.337 moles of calcium, 0.675 moles of oxygen, well, not O2, that's kind of misleading, just oxygen, and 0.675 moles of hydrogen. So now what do we do with these values? We know that these are going to be our actual ratios in the empirical formula. So we can just write out our preliminary answer to this problem. We can say we have calcium, write that a little bigger. We can say that we have calcium, 0.337, oxygen, 0.675, and hydrogen, 0.675. But something is weird about this formula. We don't like having decimals as our subscripts. So in order to get these to whole numbers, we can really multiply or divide this by whatever we want as long as we do it to everything. So the easiest way to get this to a whole number ratio is to just divide by the smallest subscript. And the smallest subscript is 0.337. So we divide everything by 0.337. And we end up getting a really neat answer. It ends up being calcium, just 1, so we write nothing. Oxygen, there's 2 of those. And hydrogen, there's 2 of those. And this is actually going to be the base, calcium hydroxide. So you're going to notice that when you do these divisions, you're always going to end up with whole number ratios. And these don't work out exactly all the time. Sometimes you're going to get like 2.01 or 1.999, and that's fine. You're always going to easily be able to tell what whole number to round it up to. It's going to be very close. And the only reason you would have non-whole numbers when you finish your division is because of rounding differences. Like, it's always going to be a whole number. There's always going to be an easy, straightforward way to get to whole number ratios from this. So now we know that the empirical formula for this compound with this percent composition is going to be this. We have a calcium hydroxide. So now that we've found the empirical formula of this compound, it is calcium hydroxide. Now we can look at the molecular formula. So the reason the molecular formula cannot be found just purely by experiment is because you need one additional piece of information. You need the molar mass of the compound. So once you're given that the molar mass of this particular compound, calcium hydroxide, is 74 grams per mole, then you can be certain that the empirical formula is actually the same as the molecular formula. But if that was not the case, suppose we were given the actual molar mass as equal to 148 grams per mole. This is just a completely hypothetical compound. I don't know if it exists. It probably does not. But suppose the actual molar mass of the compound we were given originally to find the formula for was 148 grams per mole. So looking at the masses of all the elements in calcium hydroxide, we add up all the molar masses and we get to a total molar mass of this compound of 74 grams per mole. Now this is not the same. So that's when we know that the empirical formula and the molecular formula are going to be different for that compound. And we just look at this logically. 148 is twice of 74. So that means we need to multiply this formula by 2 in order to get to the actual formula. So the actual formula in this case would be Ca2OH4. Like I said, I don't think this actually exists, but it's just an example to show you how you would find the molecular formula. Just whenever you have your molar mass given, you find the molar mass of the empirical formula, you find out how many times that goes into the actual molar mass, and you multiply your empirical formula by that many times. So that's really all we have for empirical and molecular formulas. I know that was kind of a quick and easy video, but next up we are going to be doing organic nomenclature, so that's going to take a while, so get ready for that.